Hello viewers, welcome to online course on Mathematics 3. This course basically for undergraduate student or BTech student of engineering field. Today we are going to discuss about the divisibility and division algorithm of number theory. Myself Sanjay Vishwas, Assistant Professor of Mathematics of Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is my details of contact information. If you have facing any kind of problem regarding my online class, you can call me or send message through my mail ID sanjay.vishwas@gnit.ac.in. Before we start today's lecture, let's quickly recall the last lecture. So in the last lecture we have discussed about the Weyl ordering principle and fundamental theorem of arithmetic. So in this lecture we have talked about the introduction of Weyl ordering principle, and after that we have discussed about the natural number, and you know the natural number there are 1, 2, 3, 4 and up to infinity. Okay, and natural number are the numbers that used for counting. And after that we have talked about the mathematical induction and the proof of mathematical induction and statement. And then we have talked about the complete induction, that means the inductive idea can be pushed into some interesting places. Okay, so where the induction, that means the complete induction are used. And after that we have discussed about the Weyl ordering principle. This is the most important part of number theory, and some related examples we will discuss on Weyl ordering principle and fundamental theorem of arithmetic. Okay, so after that we have talked about the integers and induction. So today we are going to discuss about the divisibility and division algorithm of the module number theory of the course Mathematics 3. So this is my second lecture on number theory, and this is a very important part of number theory as well. Here is the content of today's lecture. So first of all we will discuss about the introduction to divisibility. And after that we will study on the properties of divisibility. So there are some properties of divisibility, and then we will talk about the division algorithm. So here is the statement and proof of division algorithm we will discuss in lecture 2. Then we will talk about the theorem on divisibility. So there are some theorem related to divisibility of a number theory we will discuss in lecture 2. And after that we will talk about some examples on divisibility and division algorithm of number theory. So let us begin with the introduction of divisibility. So here is the introduction. So the number theory concerned itself with studying the multiplicative and additive structure of natural number. So multiplicative and additive structure, and they are the binary operation of natural number, and the natural number they are 1, 2, 3 and up to infinity. Okay, so they are all natural numbers. So frequently the number theoretic question are better asked in the set of all integers. So 1, 2, 3, that means plus minus 1, plus minus 2, plus minus 3 and up to infinity. They are all integer. Okay, so and the positive integer are known as the natural number, and the set of the numbers 0, plus minus 1, plus minus 2, plus minus 3, this is called the set of all integers. Okay, so and it is denoted by capital Z, and Z is equal to within second bracket 0, plus minus 1, plus minus 2, plus minus 3 and up to infinity. This is the collection of numbers. Okay, is called the set and set of integers. And the better answered by making use the rational numbers. Okay, and you know the set of natural number is a subset of set of integer. So in that case, where z is bigger than the set of natural number. So after that, the rational number, and you know the rational number can be written as p by q, where p is belongs to z. Okay, so you know p is belongs to the set of integer, and q, it is the set of natural number. Okay, so p by q, where p and q are the relatively prime, then the rational number, it is equals to p by q. Okay, and the set of natural number and the set of integer, they are all subset of set of rational number. Okay, and the set of real number, it is denoted by capital R, and set of rational number, it is a subset of set of real number. As well as the complex number, it is denoted by capital C, and set of real number, it is a subset of set of complex number. Okay, so and more structure may become apparent. So some from the numbers theory was developed by the ancient Babylonians, Egyptian and Greeks. So the people from Babylonian, Egyptian and Greek, they are invented by some numbers theory, and applying this number theory, now many modern problems are motivated by their work. So therefore, when studying other long-standing area of mathematics such as Euclidean geometry, calculus or linear algebra, and they are all the mathematical part of number theory. And it is easy to come away with the conclusion that everything was worked out long ago. So that actually the number theory is the basic part of mathematics. And from their number theory, we have invented such as Euclidean geometry, calculus, or linear algebra. Okay, so it is easy to come from with the conclusion that everything was worked out long ago. So the number theory is not like that, and for many problems, some of them ancient, we have more conjectures than theorems. Nevertheless, a new method and result emerge in fit and start, and the subject has seen many great advance in just the last few decades. And here are a few examples of number theoretic problems that have been solved only recently or still remain open. So there are some problems that have been solved or now still open for all. Okay, so the problem there, a Fermat-Lars theorem. This is a very important part, and this theorem was proved in 20th century, and it is open for last 100 years. Okay, so here is the problem. So for any integer n greater or equals to 3, the equation x to the power n plus y to the power n is equal to z to the power n has no solution with x, y, z belongs to n. So here x, y, z, they are all integer and satisfying this equation. Okay, so that is x to the power n plus y to the power n is equal to z to the power n. And this is called the Fermat-Lars theorem. And this equation has no solution with x, y, z is belongs to the set of natural number. Okay, and n is always greater or equals to 3. Next, we will introduce the second problem, that is the congruent number problem. Okay, for which n belongs to n, where n is lies in capital N, where capital N is the set of natural number. You know, is there a right angle triangle with rational side and area n, where 2n is equal to x into y, with x square plus y square is equal to z square. This is actually the Pythagoras theorem. X square plus y square is equal to z square, where x, y, z is belongs to q. Okay, so this is the second problem, that is the congruent number problem, for which n belongs to capital N. Is there a right angle triangle with rational side and area small n, where small n, that means 2 into n, it is equals to xy, and with the relation x square plus y square is equal to z square, where x, y, z is belongs to set of rational number. So such as n congruent number, for instance 6 is a congruent because it is the area of the form 3, 4, 5 right angles. So that means 3, 4, 5 these are the they are the base, height and hypotenuse. Okay, so but it can be shown that 3 is not the congruent number. This is the second problem on number theory. So this following problem are either solved or remain open for all. And now move on the third problem. So this problem is actually the Catalan's conjectures. The only consecutive power of natural numbers are 8 and 9. That means x to the power n minus y to the power n, it is equals to 1. Okay, this is the third problem on number theory. So move on the fourth problem, and this is actually the twin prime conjecture. So the problem is there are infinitely many pair of prime numbers that differ by 2. And the fifth problem, it will be Goldbach conjecture. So every integer x greater than 1 can be expressed as the sum of at most 3 prime numbers. So these following problems are either have been solved recently or still open to all. So now move on the next slide. So in this slide we will discuss about the divisibility of number theory. So here is the definition. Suppose that be two numbers, it belongs to Z. So a, b, be two integers. Okay. So we say that b divides a, and we can write it b slash a. Okay. This is the symbol of divisibility. So here b divides a. So when there exists a number c is belongs to Z such that a is equal to b into c, then from this we can say that b divides a. So in such circumstances we say that a is a divisible by b, or that b is a divisor of a. Okay, so either you can say a is a divisible by b, or you can say b is a divisor of a. So you know that these two part are mathematically same. Okay, that means a is a divisible by b, or b is a divisor of a. So when a is not divisible by b, then we can write a does not divisible by b. This is the symbol. It is does not divisible by b. And when b is divided a and 1 less or equal to b less than a, that means b lies in 0, 1 to a, then we say that b is a proper divisor of a. So these are the properties of the divisibility. And when we write a to the power k is parallel to b, then a to the power k is divised b, but a to the power k does not divide b. Either a to the power k divides b, or a to the power k does not divide. Then we say a to the power k is parallel to b. And it is understood that b divides a makes sense only when b is non-zero. Otherwise it is not possible. Okay, so that means when b is 0, then b divides a, this is undefined. Okay, and it is possible only when b is non-zero. So there is a note on divisibility. When b divides a, then b is called the divisor or the factor of a, and a is called the multiple of b. Okay, and if b divides a, then minus b, it is also device 10 because a is equal to b into c, you know that. So you know this is the definition of divisibility, but b divides a, then there exists a number c belongs to z such that a is equal to b into c. Okay, this equation can be written as a is equal to minus b into minus c, and you know that the multiplication of minus b into minus c is equals to b into c. So a is equal to bc can be written as this. Okay, and where you know minus c is an integer, so a is equal to minus b into minus c, it is also written as a is equal to minus b into k, say, where k be an integer. So therefore, from the definition of divisibility, we can say that minus b divised a. So therefore, b divised a implies minus b divised a. Now move on the next slide. So in this slide, we will discuss about the properties of divisibility. Okay, there are some properties or theorem on divisibility. So for all numbers m, n and d. Okay, so where d divides 0, this is the first property of divisibility. 0 divides 10 implies n is equal to 0. And the third property, it will be 1 divides 10. Okay. Fourth property, this is called the reflexivity property, and that means n divides 10. This is exist. And the fifth property, it will be n divides 1, and this imply n is equal to 0 or n is equal to minus 1. Now move on the sixth property of divisibility. This is called the transitivity property. That means d divides 10 and n divides m, and combining these two implies d divides m. So now move on the seventh property of divisibility. This is called the multiplication property. That means d divides 10 imply ad divides a, where a be any numbers. Now move on the next property. So this is called the cancellation property. Okay, so that means ad divides 10 and a is not equals to 0, then d divides 10. And after that we are talking about the linearity property, and it is actually the d divides 10 and t divides m. So mn are the numbers. Okay, and this is the different number where n is not equals to m, and this imply d divides an plus bm for all a and b. So after that we will move on the 10th property, and it is called the comparison property. So if d and n are positive and d divides 10, then d is less or equal to n. Okay, so these are the properties of divisibility. Now we are going to prove the above properties of divisibility. So here is the proof. So for the first item, that is d divides 0. So you know that 0 is always divisible by any number. So that is for the first item, take k is equal to 0. So that means 0 is divisible by any number. That means d. So now we take k is equal to 0. So for the second properties, that means 0 divides 10, and this implies n is equal to 0. Okay, that means for the second item, if 0 divides n, so then n can be written as n is equal to 0 into k, and you know that k is equal to 0, so 0 divides n. Okay, so this is the proof of the second property. And the next item, that means 1 divides 10. So 1 is always divides any number. So that means the next item will hold. When we take k n as kth definitions. And now move on the fourth property, that means the reflexivity, and this is similar when we put n is equal to n into 1. Okay, so where 1 is any integer or any numbers. So from the definition of divisibility we conclude that n divides 10, and this shows that it holds. So the next property follows immediately from the basis axiom 3 for Z. So that means n divides 1 is implies n is equal to 0 or n is equal to minus 1. Now move on the sixth property, that means the transitivity. So assume that d divides 10 and n divides n. So from the first one, that means d divides 10, and from the definition of divisibility it can be written as n is equal to d into k1, where k1 be any integer, and n divides 10 and it can be written as m is equal to n into k2 for some integer k2. Okay, so where k1 and k2 are two integers and it is belongs to z. Okay, where z is a set of integers. Now substituting n in the second equation, that means m is equal to n into k2. So from this we will get m is equal to dk1 into k2, where n is equal to dk1. Okay, so while k1 and k2 both are the integers, so now applying the associativity properties of the multiplications, we get dk1 k2 and it is equals to d into k1 k2. Okay, so where k1 k2 is in first bracket, and which shows that d divides m, where k1 k2 is integer. Okay, so from the definition of divisibility it shows that d divides m. This is the proof of the sixth property, that means transitivity. So now move on the seventh property, and it is actually, this is the seventh property, multiplication property. That is d divides 10, it is implies ad divides a. Okay, so now we will move on the proof of these properties. So here is the proof of the seventh property. So the multiplication also follows from associativity. That is, assume that d divides 10, and so that from the definition of divisibility it can be written as n is equal to d into k, where k be any integer. So now multiple by a on both sides. On this equation we will get a n, it is equals to a into d into k. Okay, so now applying the associativity property of the multiplication, we get a into d into k can be written as ad into k, where k be any integer. So now from the definition of divisibility it can be written as ad divides an. Okay, this is the proof of the sixth property, that means the multiplication properties of divisibility. So now move on the seventh property, and this is the seventh property, the cancellation property. That means ad divides n, and when a is not equals to 0, then from this we will get d divides 10. Okay, this is called the cancellation property. So here is the proof of the cancellation property. So for cancellation property, assume that a is not equals to 0 and that ad divides 10. So from the definition of divisibility, there exists a integer k such that an is equal to ad into k. So it can be written as this, and we will show that n is equal to d into k. That means d divides 10 from this. Assume first that a is greater than 0. So by the tracheotomy properties from the first appendix, either n is greater than dk, or n is equal to dk, or n less than dk. Okay, so there are three cases. So first case, when n is greater than dk, or n is equals to dk, or n is less than dk. Now the first case, it will be n greater than dk. Okay, so when n greater than dk, then we have a n greater than a into dk, and applying the associativity property, we will get ad into k. A into dk, it is equals to ad into k, where AD within first bracket, and which contradict this paragraph's assumption that AN is equal to AD into K. This is given, but when we take n greater than dk, then from this we will get AN greater than AD into K. So this is not possible. Okay. Now if we take n is less than dk, then from the above equation we will get AN less than A into dk. And now applying the associativity property, we will get AN is less than AD into K, where AD is in first bracket, which is also contradicting the assumption. So therefore n is equal to d into k. So when we take n greater than dk, then it is not possible. This is the contradict our assumption. When n is less than dk, it is also contradict by our assumption. So therefore n is equal to d into k. It is possible, and so d divides n. So the argument for the a is less than 0 case is similar. So when a is greater than 0, then we from this cancellation property we will say d divides 10. And the argument it is also true for when a is less than 0. So now verify the linearity property. So you know this is the linearity property. D divides 10 and D divides 10, and this imply D divides AN plus BM for all AB where AB be any numbers. So this is called the linearity property. So here is the proof of the linearity property. So to verify the linearity, suppose that D divides 10 and D divides 10. So from the definition of divisibility, you know that D divides 10, it can be written as n is equal to d into k1, and d divides 10, and it can be written as m is equal to d into k2 for some k1 k2 belongs to z, that means set of integer. Okay, so therefore an plus bm and is equals to a into n, where n is equal to dk1, so a into dk1 plus b into m, where n is equal to dk2. So after putting the value of n and m, we will get an plus bm, it is equals to a into dk1 plus b into dk2. Okay. Now taking d as common, so from the above equation we will get an plus bm, it is equals to d into ak1 plus bk2. Okay. And where ak1 plus bk2, it is a integer, you know that, where ab be two numbers and k1 k2 be integers, so this is a number actually. Okay, or this is an integer. So which shows that d divides an plus bm. This is the definition of the divisibility. Okay, so finally for the comparison, assume that dn is greater than 0 and d divides 10. This is the last property of divisibility. Okay, so when d and n greater than 0 and d divides 10, then you know from the divisibility we can write n is equal to d into k for some integer k. Okay, so observe that k is positive because the other two are positive. So here d and both the terms are positive, so k is a positive too. So by trichotomy, either d is less than n, or d is equals to n, or d is greater than n. So we will show that the d greater than n case is not possible. So assume that d greater than n, and then when k be any integer and it is greater than 0, then dk it is also greater than n into k. Right? And it follows by one of the first appendix properties of the inequality, but that gives n greater than, but dk is equal to, you know that dk is equal to n, so n greater than n into k, and which mean that n into 1 it is greater than n into k, and despite the fact that k is positive and so 1 is lesser equal to k. Okay, so this is impossible because it violated the same properties of inequality. That means D is lesser equal to N. This is the proof of the comparison properties of divisibility. Now move on the next slide. So in this slide we will discuss about the examples of divisibility. So here is the example. Prove that if x is even, then x square plus 2x plus 4 is divisible by 4. Okay, so this is the example of divisibility. So here is the solution of the above example. X is even, that means 2 divides x. X is even number, that means x is always divisible by 2. Okay, that means 2 divides x. And from this we will prove that x square plus 2x plus 4 is divisible by 4. Okay, so you know that 2 divides x and 2 divides x, and this implies 4, that means 2 dot 2, that means 2 into 2 divides x into x. This is the one of the properties of divisibility. If A divides B and C divides D, this implies AC divides BD. That means 2 divides x and 2 divides x, and applying these properties of divisibility will get 4, that means 2 into 2. So 2 into 2, that is 4 divides x into x, that means x square. Okay, that is 4 divides x square. Now move on the next part, that means 2 divides 2 and 2 divides x, and this imply 2 into 2, that means 4, it is divided 2 into x, that means 2x. The same properties apply in that case, that means if A divides B and C divides D, then AC divides BD. Okay, so 4 divides 2 into x, and obviously you know that 4 divides 4. 4 is always divisible by 4. So for the first case where x square is divisible by 4, for the second case where 2x is divisible by 4, and for the third case where 4 is divisible by 4, that means 4 divides x square, 4 divides 2x, and 4 divides 4. So therefore, by the linearity property, then from the above two part, that means 4 divides x square and 4 divides 2x, then applying the linearity property will get 4 divides x square plus 2x. So you know that the linearity property is actually d divides 10 and d divides 10, and from this we will imply d divides a plus b for all a and b. So therefore 4 divides x square plus 2x, and 4 divides x square plus 2x and 4 divides 4, then applying the linearity property again we get 4 divides x square plus 2x plus 4. So therefore 4 divides, after simplifying this we will get 4 divides x square plus 2x plus 4, that means x square plus 2x plus 4 is divisible by 4. Hence the proof of the above examples. So after that we will discuss about the division algorithm. Okay, this is the definition of division algorithm. If a and b are integers such that b greater than 0, then there exists a unique integer q and r such that a is equal to bq plus r, but 0 lesser equal to r less than b. That means r is lies in 0 to b. So in that case, where q is the quotient and r is the remainder. So here is the proof of the above theorem. So consider the set A, and A is equal to A minus B into K. It is greater or equals to 0, such that K be any integer. That means it is belongs to Z. And note that A is non-empty since you know A minus B K is greater or equals to 0 and K is less than A is like B. So by the well ordering principle, A has the least element, say R, and R is equal to A minus B into Q for some Q. And notice that R is greater or equals to 0 by construction. So now if r greater or equals to b, then r greater than, and you know b is greater than 0, so r is greater than r minus b, and you know r is equal to a minus bq and a minus bq minus b. So therefore from this we'll get r is greater than a minus, where b as a common from the last two terms we will get. So therefore r is greater than a minus b into q plus 1. It is also greater than or equal to 0. So this leads to the contradiction since r is assumed to be the least positive integers of the form a r is equal to a minus b into q. So as a result we have 0 less than or equal to r and less than b. It is also given, and we will show that q and r are the unique. Okay. So suppose that a is equal to bq1 plus r1 and a is equal to bq2 plus r2, where r1 is lies in 0 to b and r2 is also lies in 0 to b. Then we have b into q1 minus q2 plus r1 minus r2, it is equals to 0. Okay, so therefore as a result b into q1 minus q2 it is equals to r2 minus r1. So from the above equation we will conclude that is b into q1 q2 is equal to r2 minus r1. Okay, so thus we get from the above r is devised r2 minus r1, and since minus max of r1 r2 less or equal to r2 minus r1 within modulus less or equal to max of r1 r2, and where b is greater than max of r1 r2, then r2 minus r1 must be 0. That is r2 is equal to r1. And since bq1 plus r1 is equal to bq2 plus r2, where r1 and r2 both are equal, then from this we will get q1 is equal to q2. And this proves the uniqueness, that is q and r both are unique, where q is the quotient and r is the remainder for the division algorithm. Okay, so if we take a is equal to 71 and b is equal to 6, then from the division algorithm it can be written as 71 is equal to 6 into 11 plus 5, where q is the quotient, it is equals to 11, and r is the remainder, it is equals to 5. Now we are going to talk about some examples on division algorithm. So here is the example. Use division algorithm to prove that the square of an odd integer is of the form 8k plus 1 where k is an integer. Okay, this is the examples of the division algorithm. So here is the solution. So by the division algorithm, you know that every integer upon division by 4 leaves one of the remainder. Okay, when we divide it by 4 for any number, there are 4 remainders. That means they leaves one of the remainders 0, 1, 2 and 3. So therefore any integer is of the form 4q, okay, where q be any integer, or 4q plus 1 or 4q plus 2 or 4q plus 3, where q be any integer. So any number which is divisible by 4, then it is of the form 4q or 4q plus 1 or 4q plus 2 or 4q plus 3, where q be any integer. Okay. So odd integer are of the form, so among these the odd integer they are 4q plus 1 and 4q plus 3. These two are the odd integers. Okay. So from this we will show that the square of odd integers is of the form 8k plus 1. Okay. So 4q plus 1 whole square, it is of the form 8k plus 1, and 4q plus 3 whole square, it is of the form 8k plus 1. Okay, where k be any integers. So these two are the odd integers. So here 4q plus 1 whole square, it is equals to that 16q squared plus 8q plus 1. Okay, so from the first two terms we will take 8 as a common, then from this we will get 8 into 2q square plus q plus 1. Okay, where q is a integer, then 2q square plus k, it can be written as k, where k be any integer. So 4q plus 1 whole square, it can be written as 8k plus 1 where k is equal to 2q square plus q. That means 4q plus 1 whole square is of the form 8k plus 1. Similarly, 4q plus 3 it is also the odd integer. Okay, so 4q plus 3 whole square is also equals to 8 into 2q square plus 3q plus 1 plus 1. Okay, when we simplify this one, that means 4q plus 3 whole square, this is equals to 16q square plus 4 into 3 12 into 2, that means 24 into q plus 9. Okay, so and it can be written as this 8 into 2q square plus 3q plus 1 plus 1, and it is of the form 8k plus 1, but k is equal to 2q square plus 3q plus 1. Okay, so hence the square of an odd integer is of the form 8k plus 1. So hence the proof of the above examples. Now move on the second example on division algorithm. So here is the example. Prove that the product of any consecutive integers is divisible by n. Okay, so here is the proof. Let us consider the consecutive integers be c plus 1, c plus 2, c plus 3 and up to c plus m minus 1. So there are m numbers of consecutive integers. Okay, and they are this. And let q be the quotient and r be the remainder, and c is divided by m. Then from the division algorithm it can be written as c is equal to mq plus r, and where r is lies in 0 to m. Okay, so when r is equal to 0, then from the above we get c is equal to mq, and therefore m is divised c where q be any integers. Okay, so from the definition of divisibility we will get m divised c. So now when r is equal to 1, then from the above we get c plus m minus 1, it is equals to m into q plus 1. So in that case where m minus 1 be added on both sides, we get c plus m minus 1, it is equals to m into q plus 1. And from the divisibility we will get from this m divised c plus m minus 1. Okay, again we put r is equal to 0 and added m minus 2 on both sides, we will get c plus m minus 2, it is equals to m into q plus 1. Again from the divisibility theorem we will get m divised c plus m minus 2. Okay, and similarly when we take r is equal to m minus 1, then from the above equation, that means from the division algorithm we will get c plus 1, it is equals to m into q plus 1. Okay, and therefore m divised c plus 1. So therefore whatever integer r may be, and m divised one of the integers c plus 1, c plus 2, c plus 3 and up to c plus m minus 1, and it follows that the product, that means c into c plus 1, c plus 2 and up to c plus m minus 1, it is always divisible by m. So and m divides c plus m minus 1, m divides c plus m minus 2, and their product. So there is a properties of the divisibility, that c into c plus 1 into c plus 2 and up to c plus m minus 1, it is also divisible by m. Hence the proof of the second example of division algorithm. So I will stop here today's lecture. Thank you.